let's see if we can use our knowledge of Green's theorem to solve some actual line integrals. And actually, before I show an example, I want to make one clarification on Green's theorem. All of the examples that I did is I had a region like this. And the inside of the region was to the left of what we traversed. So all my examples, I went counterclockwise. And so our region was to the left of, if you imagine walking along the path in that direction, it was always to our left. And that's the situation in which Green's theorem would apply. So if you were to take a line integral along this path, the closed line integral, maybe we could even specify it like that. You'll see that in some textbooks. Along the curve C of f dot dr, this is what equals the double integral over this region R of the partial of q with respect to x minus the partial of p with respect to y d area. And just as a reminder, this q and p are coming from the components of f. F in this situation, f would be written as f of xy is equal to p of xy times the I component plus q of xy times the j component. So this is a situation where the inside of the region is to the left of the direction that we're taking the path. If it was in the reverse, then we would put a minus sign right here. If this arrow went the other way, we'd put a minus sign, and we can do that because we know that when we're taking line integrals through vector fields, if we reverse the direction, it becomes the negative of that. We showed that, I think, 4 or 5 videos ago. With that said, it was convenient to write Green's theorem up here. Let's actually solve a problem. So let's say I have the line integral. And let's say we're over a curve. I'll define the curve in a second. But let's say that the integral we're trying to solve is x squared minus y squared dx plus 2xy dy. And then our curve, they're giving us the boundary. The boundary is the region. I'll do it in a different color. So the boundary of, so the curve is boundary of the region given by all of the points xy such that x is greater than or equal to 0, less than or equal to 1, and then y is greater than or equal to 2x squared and less than or equal to 2x. So let's draw this region that we're dealing with right now. So let me draw my x-axis, or my y-axis, sorry. My y-axis, and then my x-axis right there. And let's see, x goes from 0 to 1. So if we make, that's obviously 0. Let's say that is x is equal to 1. So that's all the x values. And y varies, it's above 2x squared and below 2x. Normally, if you get to large enough numbers, 2x squared is larger. But if you're below 1, this is actually going to be smaller than that. So the upper boundary is 2x. So it's 1, comma 2. This is the line y is equal to 2x. So that is the line y is, let me draw a straighter line than that. The line y is equal to 2x looks something like that. That right there is y is equal to 2x. And then this bottom curve, maybe I'll do that in yellow. And then the bottom curve right here is y is going to be greater than 2x squared. It might look something like this. And of course, the region that they're talking about is this. But we're saying that the curve is the boundary of this region, and we're going to go in a counterclockwise direction. I have to specify that. Counterclockwise direction. So our curve, we can start at any point really, but we're going to go like that, and then get to that point, and then come back down along that top curve, just like that. And so this met the condition that the inside of the region is always going to be our left, so we can just do the straight up Green's theorem. We don't have to do the negative of it. And let's define our region. So our region, let's just do our region. If this integral right here is going to go, I'll just do it the way y goes from y. Let me do it. Y varies from y is equal to 2x squared to y is equal to 2y is equal to 2x. And so maybe we'll integrate with respect to y first, and then x, I'll do the outside, x, the boundary of x goes from 0 to 1. So they set us up well to do an indefinite integral. And now we just have to figure out what goes over here. Green's theorem. This right here is our f. It would look like this in this situation. F of xy is going to be equal to x squared minus y squared I plus 2xyj. We've seen this in multiple videos. You take the dot product of this with dr, you're going to get this thing right here. So this expression right here is our p of xy. That is our p of xy. And this expression right here is our q of xy. Q of xy. So inside of here, we're just going to apply Green's theorem straight up. So the partial of q with respect to x, the partial of q with respect to x. So take the derivative of this with respect to x, we're just going to end up with a 2y. So we're going to end up with a 2y. And then from that, we're going to subtract the partial of p with respect to y. So if you take the derivative of this with respect to y, that becomes 0. And then here, you have the derivative with respect to y here is minus 2y. Right? Minus 2y. So you have a minus 2y, just like that. And so this simplifies to 2y minus 2y. That's 2y plus 2y. I'm just subtracting a negative. Or this inside, and just to save space, this inside, that's just 4y. So I don't want to have to rewrite the boundaries. So that right there is the same thing as 4y. The partial of q with respect to y, 2y, minus the partial of p with respect to y, which was minus 2y. You subtract a negative, you get a positive, you have 4y. So let's take the antiderivative of the inside with respect to y, and we're going to get 2y squared. Let me do it a little bit lower. We're going to get 2y squared, right? If you take the derivative of this with respect to the partial with respect to y, you're going to get 4y. And we're going to evaluate that. We're going to evaluate that from y is equal to 2x squared to y is equal to 2x. And of course we still have the outside integral still there. X goes from 0 to 1 dx. This thing is going to be equal to the integral from 0 to 1. And then we evaluate it first at 2x. So you put it 2x in here. 2x squared is 4x squared, right? 2 squared, x squared. So 4x squared times 2 is going to be 8x squared. 8x squared minus, put this guy in there. 2x squared squared is 4x to the fourth. 4x to the fourth times 2 is 8x to the fourth. 8x to the fourth. Did I do that right? 2x squared. We're going to put it there for y. Substitute y with it. That squared is 4x to the fourth times 2 is 8x to the fourth. Very good. All right. Now dx. Now this is just a straightforward one-dimensional integral. This is going to be equal to, I'll just do it here. This is going to be equal to the antiderivative of 8x squared is 8/3 x to the third. 8/3 x to the third. And then the antiderivative of x to the 8x to the fourth is minus 8/5 x to the fifth. 8/5 x to the fifth. And we're going to have to evaluate that from 0 to 1, or give a little line there sometimes. 0 to 1. When you put 1 in there, you get, I'll do it in a different color. We get 8/5 times 1 to the third, which is 8/5, minus 8/5, minus 8/5. And then we're going to have minus, when you put 0 in here, you're just going to get a bunch of zeros. Oh, sorry, I made a mistake. It's not a, it's been a blunder. It's 8/3. 8/3. 8/3 times 1 to the third minus 8/5 times 1 to the fifth. So that's minus 8/5. And then when you subtract the 0, so then minus, you evaluate 0 here, you're just going to get a bunch of zeros. So you don't have to do anything else. So now we just have to subtract these two fractions. So let's get a common denominator of 15. 8/3 is the same thing if we multiply the numerator and denominator by 5. That is 40 fifteenths. And then if we multiply this numerator and denominator by 3, that's going to be 24 over 15. So minus 24 over 15. And we get it being equal to 16, right? 16 over 15. And so using Green's theorem, we were able to find the answer to this integral up here. It's equal to 16 15. Hopefully you found that useful. I'll do one more example in the next video.